I hope I am audible. Am I audible clearly?
Yes, ma'am. Audible.
Yeah, thank you. Thank you. Thank you so much. Okay, students. So far we discussed structure of artificial neural network, basic building block of neural network. Then we also discussed how neural networks learn representations from data. Then we saw shallow neural network and single and multi-layer perceptrons. So we have seen this topic so far, and by now I hope it is clear that neural networks are used by machines to learn representations from data. And data may be in any format. It may be in text format, it may be in image format, it may be voice data. So these neural networks are used to learn representations from data because we want to automate tasks. So machines need to learn when we expect machines to do to complete those tasks, right? Okay, so I realized from your questions in last two classes that some of you have not learned machine learning, and that's why first time they have learned these three machine learning techniques, which are supervised learning, unsupervised learning, and reinforcement learning. I advised you to go through these techniques, and I hope by now you have gone through these techniques in detail and the concepts are clear to you that what is supervised, unsupervised, and reinforcement learning. Right. However, today I will also tell you the differences between them again because I realized from last two classes that some of you have not studied these subjects and I believe that it's very difficult to proceed in this subject if you have not studied machine learning, like at least fundamentals of machine learning. Okay. And I also discussed with your professors that they will cover some of the topics in brief, not in possible because then it's an entire subject. So even if they cover in brief, you can explore those topics in depth on your own. Fine. So we have seen this artificial neural network and basic structures like shallow network, layer, perceptron, and multi-layer perceptron. Now, moving further, today I would like to discuss hyperparameters and parameters associated with neural network. This topic is not specifically mentioned in your first unit, but this is required. It is required to understand these parameters because when we want to learn from data, we use neural network, and these are all parameters associated with neural network. Probably you have heard some of these parameters in our previous discussion, like weights, bias, hidden layer, neuron. So this you're familiar with these terms, but some of the parameters are new to you, like batch size, learning rate, number of epochs, activation function, optimizer, loss function. These are all very important parameters associated with neural network. So today let us discuss these parameters. Now, let us first discuss what is the difference between parameters and hyperparameters associated with neural network. Okay, so let me define briefly that parameters are the parameters like this. These are also called model parameters because neural network, we have different architectures for neural network and they are called neural network models. So when I use the term model, I mean that it is neural network, some specific neural network architecture. Fine. So model parameters are the parameters that are estimated by the model, that is by the neural network from the given data. So these two parameters, weights and bias, they are estimated by the neural network from the given data. Right? We may have we have different data sets for different problems for different real life sectors. So this two parameters are estimated by neural network from the given data. Now, what is model hyperparameter? These are the parameters that cannot be estimated by the neural network from the given data, but these parameters are used to estimate the model parameters. These parameters are used to estimate these two parameters. Okay, these are the model parameters. So these hyperparameters are used to estimate the model parameters. So see, I am repeating, these parameters are also used, these parameters are estimated by from the given data, as well as we can also use hyperparameters to estimate these parameters. So these two are different, like these are parameters and these are hyperparameters. Let me tell you the differences between these two. The differences are that, as we have just discussed, these are required for making predictions. These parameters and these hyperparameters are required for estimating the model parameters. So these are the model parameters. So hyperparameters are required when we want to estimate these two model parameters. And these are required when we want to make actual predictions, when we actually use that trained neural network in our real life sector. So once we train neural network, we use it, we deploy it for our application. So when we use it in our application, it is used to make the predictions. Fine. The next difference is these parameters are estimated by optimization algorithms like gradient descent, Adam, Adagrade, etc. While these hyperparameters are estimated by hyperparameter tuning. So I'll discuss what is hyperparameter tuning after the discussion of this differences. Okay. The next difference is model parameters are not set manually. Okay, listen, they are not set manually. While these hyperparameters, they can be set manually. They can also be set using some methods, but they can also be set manually. The next difference is that the final parameters found after training, because this parameters, we get optimal value of these two parameters once the training of that neural network gets over. So once the training of that neural network gets over, we get the final values of weights and after the training, they decide perform on future data, on unseen data, that new data. Very important, like we want to get optimal value, we want to get best values, weights and bias. It depends that we tune our hyperparameters, because these hyperparameters are used to estimate. So if we set these hyperparameters properly, and if we get their optimal values, then we will also get optimal values for weights and bias, and they will help us to perform efficiently for unseen future data. While these hyperparameters, the choice of hyperparameters decide how efficient the training is. So these are used during the training, okay? And based on this values will be updated, and finally we will have good values for this weights and bias at the end of training. The choice of hyperparameters decide how efficient the training is. And in gradient descent, the learning rate decide how efficient and accurate the optimization process is in estimating the parameters. So these are the fundamental differences between model parameters and model hyperparameters. I hope they are clear, like how they differ from each other. Fine. Okay. Now, let us briefly talk about the weights and bias, because as I told you, it is expected that this term should be clear to you, because machine learning is prerequisite for this subject. But however, those who are new to the subject, like machine learning or deep learning, I'll introduce this weight in brief, that what is it. Okay, so when we start training neural network, we initialize weight. So there are different techniques to initialize this weight values. Let us consider that there is a neural network having one input layer, one output layer, and some hidden layers. Okay. Now here we have, let us assume that W represents weight matrix, and a small b is a notation used to represent bias vectors of, okay, bias vector. Fine. Now there are two techniques usually used in practice to initialize these two parameters, zero initialization and random initialization. So what is zero initialization and what is random initialization? If we talk about the zero initialization, as its name suggests, all the weights are assigned zero as the initial value is zero initialization. All weights are assigned zero value. And this kind of initialization is highly ineffective as neurons learn the same feature during each iteration because we have initialized weights with 0. So what's wrong here? That when we initialize all weights with 0, the neurons learn the same feature during each iteration. Rather, during any kind of constant initialization, the same issue happens to occur if we initialize all weight values with the same value. Like 0, when we initialize weights with 0, all weight values are 0, W1 to Wn. Okay. Similarly, like any kind of constant initialization, the same issue happens. That issue is the same feature, learns the same feature during each iteration. Thus, constant initializations are never preferred. Such constant initializations are never preferred. I could have discussed this topic in detail, but then it will take entire one class. So I'm not discussing in detail, but you will find good examples that what happens if we set 0, like with example, I could have covered that what happens with 0, what is the effect. Okay. But I'm not covering because otherwise this will take entire one class. Okay, now let us discuss the random initialization. To overcome the shortcoming of that 0 or constant initialization, random initialization assigns random values except for zeros as weights to neurons. However, in this assigning values randomly to the weights, when we assign values randomly to weights, problems like overfitting may occur. Problems like vanishing gradient problem, exploding gradient problem, they might occur. Right. So both these two techniques of initializing weights, they have their own pros and cons. When we initialize with constant value or 0 value, the neural network will learn the same feature during each iteration. That is the problem. To overcome this, we can initialize weights with random values. Now, when we assign random values, then it may occur sometimes that overfitting may occur, vanishing gradient problem or exploding gradient problem may occur. Right. So this usually you learn in machine learning. So those who have learned machine learning, I'm sure they know what are these problems. And those who are new, they need to learn that what is that. Now, again, in random initialization, it can further be divided into categories: random use in normal use in a uniform distribution. Now, this also a related subject, data mining or data science related subject, that what is normal distribution, what is uniform distribution of data. Okay, so these are the different distributions, and this random initialization of weights is further divided into categories: random normal or random uniform. Only differences in random normal weight values are initialized from normal distribution 0 to 1, values between 0 to 1, and in this random uniform in a uniform distribution. So this is about the weights. Okay. Bias, I think I will discuss later, or I can tell you in brief that what this bias is. In general practice, biases are initialized with 0 and weights are also initialized with random, weights are initialized with random numbers, right? So bias later when it is required, I'll discuss it again because otherwise you'll forget, like it is sufficient to discuss about the weights at present. Fine. So bias usually it is initialized with 0. Fine. Now, there are, apart from these two traditional techniques to initialize weights, there are other techniques available in literature, and they are like new initialization techniques. So you can refer them from literature, that which are the he technique is there, and some other techniques are there. So to overcome the limitations of this 0 initialization technique and random initialization techniques, some other methods have also been discussed in literature. But these are the two common techniques and traditional techniques to initialize weights, and they are popular. Okay, they are used in practice. So I discussed them briefly. Fine. Now let us discuss about the hyperparameters. What is hyperparameter tuning and why is it important? So these are all hyperparameters related to neural network. And I'll tell you that what is hyperparameter. See, these are the hyperparameters: number of hidden layer, number of neurons per hidden layer, batch size, learning rate, number of epochs, that is number of iterations, that how many times a neural network should be trained, activation function, optimizers, loss functions. These are various hyperparameters. So the question is, what is hyperparameter tuning? It is also called hyperparameter optimization. So what is hyperparameter tuning or optimization and why is it important? Okay. Actually, a neural network has variable parameters that must be set before training neural network, and this is called hyperparameters. All those variable parameters, they are called hyperparameters. Now these values, they affect the results of the model effectively. These values which we set before training, they affect the results of model effectively. So optimal values for these parameters to obtain the base results should be found. Optimal, I'm saying optimal, okay? So finding the most optimal combination is called hyperparameter tuning, because there are multiple parameters and we want to find the optimal combination for all these parameters. So this is called hyperparameter tuning. This hyperparameter tuning is the process of finding the optimal values for the hyperparameters of neural network. And hyperparameters, they affect the model's performance and they are set before training. Okay, so hyperparameter tuning can improve a neural network's accuracy and efficiency, and it is essential for getting good results for your neural network. Okay, fine. Sorry. By mistake, I pressed it. For example, if I give you example, just we saw some of the hyperparameters. So learning rate, for example, let's talk about the learning rate. So learning rate of a model can determine how fast model learns. How fast model learns. See, again, here you can think of the analogy, like we humans, we also learn, and every one of us has different learning rate. Some of us learn fast, some of us learn slow, right? Similarly here, learning rate of the neural network, it can determine how fast the neural network will learn. The model only fits the data well if the learning rate hyperparameter is too small or too big. Model only fits the data well if learning rate hyperparameter is too small or too big. Therefore, the right balance of neural network hyperparameters is important for the model's performance. Let us take another example. Suppose let us talk about the range of number of epochs. Let us talk about the number of epochs. So initially we can set the range of number of epochs to 50 to 500. So what we do when we set this range 50 to 500, in fact, what in this case, what we do, the hyperparameter tuning process will evaluate the model's performance with each value 50, 51, 52, up to 500 and return the optimal epoch value at the end. So this is called, like, we test with different values of this parameters and we check that which is the good value for this parameter, which gives us a good result. Okay, so this is called hyperparameter tuning. Okay, now the question is how to do hyperparameter tuning and how to find the best hyperparameters. So choosing the right combination of hyperparameters requires understanding of the hyperparameters and the business use case, that real life use case. However, technically, there are two ways to set these hyperparameters, and these two ways are manual setting of hyperparameters and automated setting of hyperparameters. So this is called manual hyperparameter tuning and automated hyperparameter tuning. Now, what is manual hyperparameter tuning? Manual hyperparameter tuning involves experimenting with different sets of hyperparameters manually. Experimenting with different sets of hyperparameters manually. That is, each trial with a set of hyperparameters will be performed by us. And this technique will require a robust experiment tracker, which could track a variety of variables from images, logs to system metrics, etc. Right? So this is very tedious job. Okay, you need to try with different values, different a set of hyperparameters, and that too with different values. And there are also a few experiment trackers that tick all the boxes. Like there are some tools like uh, Naptune.ai, W&B, Comet, MLflow. These are some of the tools using which you can like keep track of these parameters. Okay. Now, what are the advantages of this manual hyperparameter optimization? The advantages are that tuning hyperparameters manually means more control over the process, because we are like manually setting those parameters so we can see the performance, and if we want to increase from 50 to 100 we can immediately increase, right? Because manually we have full control over the process. And second advantage is, if you are researching or studying tuning and how it affects the network weights, then doing this manually would make sense, because you actually learn when you manually set these hyperparameters. So I suggest initially, when you want to learn about this hyperparameters and when you want to learn hyperparameter tuning, you should use manual setting, manual hyperparameter tuning, because then you will be able to see the effects of this hyperparameters on weight values. Our ultimate goal is we want to set good weight values using this hyperparameter tuning, right? So you will be able to see the effects of the set values on weights. So that is the advantage. Disadvantage of manual hyperparameter is manual tuning is a tedious process, because there can be many trials and keeping track can prove costly and time consuming. Yeah, that is true. Advantage is you get full control over the process, but disadvantages, many trials are required and you need to keep track of all the like trials, and like ultimately this is very costly and time consuming. Second disadvantage is that this is not a very practical approach when there are a lot of hyperparameters to consider for your neural network. So these are the disadvantages of manual hyperparameter, okay, hyperparameter setting. Okay, now let's discuss about the automated hyperparameter tuning. Automated hyperparameter tuning utilizes already existing algorithms to automate the process. And the basic steps are, okay, I have not included steps. Okay, I'll tell you the steps. There are 3 steps, 2 to 3 steps. The basic steps are, first, specify a set of hyperparameters and limits to those hyperparameters. जैसे अभी मैंने बताया था कि number of epochs के लिए range is 50 to 500. Similarly, like you decide that which parameters you want to optimize or you want to consider for your neural network. Create a set of those hyperparameters, and also create a range, create a limit for those hyperparameter, like values, set values for those parameters. Every algorithm, because every algorithm requires this set to be a specific data structure, and okay, this and dictionaries are common while, for example, dictionaries are common while working with algorithms, right? Okay, then second step is the algorithm does the heavy lifting for you. It runs those trials and fetches you the best set of hyperparameters that will give optimal results. I give you examples. Suppose these are the various hyperparameters. Let us assume I'm considering this 3 parameters: batch size, learning rate, and number of epochs. Okay. So what I may do, I may consider different values for batch size. First, I will create a set of hyperparameters which I want to optimize through training. So what is that set of hyperparameters? Batch size, learning rate, and number of epochs. Fine. Now let us set range for them. So bedside, maybe I am creating like, I'm considering different values like 32, 64, 128, and 256. Learning rate, suppose I am considering 0.0001, 0.001, and 0.1. Three values I have considered. Okay. Number of epochs, suppose I am considering 50 to 100. So there are 50 values in between, right? For learning rate, three values. For batch size, four values I have considered. And for number of epochs, I have considered 50 values because 50, 51, 52, up to 100 or 51 to 100. Okay, so what the algorithm will do, algorithm does heavy lifting. It runs all this this trials and fetches you the best set of hyperparameters that will give optimal results. So many combinations. How many combinations? 4 into 3 into 50. So all these combinations will be tried by algorithm and it will give you optimal result. And you can imagine the amount of time required to do this manually if you want to try these combinations, right? So it is very tedious job when you do manually. Okay, and now okay, so there are algorithms. Okay, fine. So now let us talk about some of those algorithms. Which algorithms are available for automated hyperparameter tuning? Only two steps are there for automated hyperparameter tuning, right? That first decide the set of hyperparameters, then set the limit, and then algorithm will try all the combinations and will give you optimal results. Fine. So which are those algorithms? These are the popular algorithms: random search, grid search, Bayesian optimization, and tree structured Parson estimators. So I hope like those who have learned machine learning, they might be familiar, but it's okay. Consider this as a revision because those who are new, they need to know all these concepts. Fine. Random search. In the random search method, we create a grid of possible values for hyperparameters. Okay. We create a grid of possible values for hyperparameters, and each iteration tries a random combination of hyperparameters from this grid, records the performance, and lastly returns the combination of hyperparameters that provided the best performance. This is how grid search works. Now, let me tell you what's the difference between grid search and random. That was random search. Now, let me tell you what is the difference between random search and grid search. Grid search method. In grid search method, we create a grid of possible value again as we create in random search for hyperparameters. Now, difference is here each iteration tries a combination of hyperparameters in a specific order. Okay, this is the difference. While in random search, each iteration tries a random combination of hyperparameters, right? While here, it tries a combination of hyperparameters in specific order. Otherwise, rest is same. You can see that the difference is very clear. You can see that on right side, I have shown both random search and grid search. In random search, you can see that we are creating possible values for hyperparameters and random combination. Okay, while here, see this x-axis represents important parameter and y-axis unimportant parameters. And you can see that here in specific order we try, while here in random order we try. So that is the difference between this random search and grid search for setting the optimized values for the hyperparameters. Okay, the next technique is Bayesian optimization. Okay, now what is Bayesian optimization? Tuning and finding the right hyperparameters for your neural network is an optimization problem. Tuning and finding the right hyperparameters for neural network is considered an optimization problem, and we want to minimize the loss function of our neural network by changing the model parameters. So Bayesian optimization helps us find the minimal point in the minimum number of steps. Find the minimum points in minimum number of steps. So this Bayesian optimization also uses an acquisition function that directs sampling to areas where an improvement over the current based observation is likely. So this is like you can refer to it in depth, that what is Bayesian optimization algorithm and how it works. The examples must be available. Okay, and the next is tree structured Poisson estimators. The idea of this tree-based estimator or Poisson optimization is similar to Bayesian optimization. Instead of finding the values of probability of y of by x, where y is the function, okay, this is a bit mathematical. But okay, in short, I may say you that tree structured Poisson optimizer is similar to Bayesian optimizer. And one of the great drawbacks of this tree structured Poisson estimator is that they do not model interaction between the hyperparameters. That said, that this TPE works extremely well in practice and was battle tested across most domains, like in many real life domains, many real life sectors. So these are the common algorithms used for automated hyperparameter tuning. Uh, I repeat that what we discussed today, we started our discussion from parameters and hyperparameters related to neural network. First, we discussed differences between parameters and hyperparameters. There are two parameters associated with neural network, weights and bias. And these parameters are estimated from data set. Moreover, hyperparameters help us to estimate these parameters. There are various hyperparameters, and here you can see the list of hyperparameters. So then how can we optimize this hyperparameters? So we discuss what is hyperparameter tuning and why this hyperparameters should be optimized, because they help us to find the good values of weights and bias. And this, when we find the optimal values for weights and bias, that help us to make accurate predictions for unforeseen data in future when we deploy the trained model for real life application. Fine. Okay, now before we proceed further, if you have any question, I would like to take your question, then we will proceed further. I usually take questions twice, once in between, almost when half of the class gets over, and then at the end of the class also. So if you have any question for the discussion so far, then I can take your question, or you can ask me questions at the end of session. So, okay, fine. I'll take your question at the end of the session because there are no question, I think. Fine. Okay, now about the different hyperparameters. The first hyperparameter is number of hidden layers. So question is how to choose a number of hidden layers. Okay, how to choose a number of hidden layers when we are formulating neural network for the given real life problem. One of the hyperparameters that change the fundamental structure of neural network is this number of hidden layers. And we can divide we can divide number of hidden layers in three situations: 0, 1 or 2, or many. First, you will not need any hidden layer if data set is linearly separable. Remember the perceptron concept we discussed in last class. Perceptron, single layer perceptron, we discussed in last class. No hidden layer. There was only one neuron, right? So if you have, and we also know that perceptron, single layer perceptron is used for linearly separable data, right? So zero hidden layer when you have a data set which is linearly separable. In fact, you don't need to use the neural network at all if all you need is a linear boundary, because neural network is for solving complex problems. So when there is only one neuron, which is called single layer perceptron, when there is only one neuron, we can say that it will help us to create a linear boundary. Okay, actually, these neural networks are used to solve very complex problems. Second, if data set is not linearly separable, then you have two choices for nonlinear data, right? Second or third. Okay, so if a data set is not linearly separable, then you need a hidden layer. And normally, a single hidden layer is sufficient because the amount that a model improves by adding these hidden layers is not significant compared to the additional work you need to do. So one is sufficient. So in many practical settings, one or two hidden layers are considered to do their job. Okay. And lastly, the third option, if you are trying to solve a complex problem, such as object classification, object detection, then you need multiple hidden layers that apply different modifications to their inputs. Okay, so that's why, like, I'll show you later in upcoming units that CNN, which we are going to learn in detail in this subject, because the subject name is deep learning for computer vision. So we will see that CNN, which is mainly used for images, right? The CNN has many hidden layers because we are performing complex tasks like object detection. We use CNN for object classification. Okay, so it is considered like one of the complex jobs. Fine. So this table shows you summary that if you have linearly separable data, you need 0 hidden layer. If you have non-linear boundaries, then you can use 1 to 2 hidden layers. And if you are dealing with complex problems, or I can say if you are dealing with images, videos, then you need many hidden layers in your neural network. The number of hidden layer, the number of hidden layers is a hyperparameter that can significantly impact the model's performance. So increasing the hidden layers can allow the model to learn more complex relationships. Increasing the number of hidden layers allow model to learn more complex relationships in data. Still, it can also increase the risk of overfitting. Like again, now this is a new term you are hearing, overfitting. Okay. There are two terms, overfitting and underfitting, related to this neural network. And like, again, I say that those who have learned machine learning, they must be familiar to these terms. If not, I'll tell you in brief after discussion of this parameters. So it is like on one side, increasing the hidden layers, increasing the number of hidden layers help model to learn more complex relationships in data. And on the other hand, increase in number of hidden layers increases the risk of overfitting. And it requires more computational resources too when you increase the number of hidden layers in your neural network. So the optimal number of hidden layers can vary based on the problem's complexity. We need to use optimal number of hidden layers, and optimal number varies from optimal number varies based on the problem's complexity and the data set size, both. Okay, problem's complexity and the size of data set. So generally, a larger data set and a more complex problem, CNN is usually used for larger data sets and more complex real-life problems. A smaller data set and a simpler problem may require fewer hidden layers, right? So for them, like, we don't need more number of hidden layers. So this is about the number of hidden layers. I hope this is clear to everyone that how to choose a number of hidden layers. Now, the next hyperparameter is how to choose a number of neurons. How to choose a number of neurons. Fine. Okay, once we decide the number of hidden layers, the next job is you should choose a number of neurons you are going to include in each hidden layer. So number of neurons per hidden layer behave similar to the number of layers. They behave similar to number of layers. The number of neurons increases with the complexity of the data. Number of neurons increases with the complexity of data. The number of neurons in neural network can vary with a chosen architecture. And here also, like, increasing neurons helps fit data better. while reducing layers can help reduce bias and faster training. When we reduce layers, number of hidden layers, they help reduce bias and faster training. Because जितने आपके layers कम उतना training faster होगा, computation would be less. Okay, so that reduces bias and it increases the speed of training. So generally, the number of neurons generally the number of neurons should be increased until there is no improvement in performance. However, finding an appropriate number is critical because too few neurons can lead to underfitting, whereas too many neurons can lead to overfitting plus longer training time. जितने neurons ज्यादा, जितने hidden layers ज्यादा, इतना computation ज्यादा, each iteration में. And you are training your neural network via several iterations. So उतना मतलब proportional आपका वो training time बढ़ेगा. So this increases the training time. Moreover, more neurons, more hidden layers, they may lead to overfitting problem. And similarly, less neurons, they may lead to underfitting problem. I'll tell you what is overfitting and underfitting after this discussion. So empirically, it is best to use a number between input and output sizes, and the number changes based on how complex your problem is. Like, there is no standard formula, frankly telling you, right? If a problem is simple and the input and output relationship is clear, then you can use 2/3 of the input size like as a good starting point, as I have mentioned in this table. Like, okay, if a problem is simple and the input output relationship is known, then 2/3 of the input size can be a good starting point. But if the relationship is complex, input and output relationship is complex, the number can vary from the input size to less than twice the input size. Input size to the less than -1 means less than twice the input size. This is when the relationship between input and output is complex. And this is like first is when relationship between input and output is simpler. Okay. So this seems vague, I know, but unfortunately there is no definite answer that you can follow, since the neural network is still an active research area and every parameter is unique to each problem. So you should just consider this as starting points and need to go through trial and error to find which value works the best for your specific problem. I hope this is clear, right? This can be only starting point, right? And then through trial and error, you can find optimal values. Fine. So this is about how to choose a number of neurons. The next is how to choose batch size, learning rate, and epoch. How to choose batch size, learning rate, and epoch, and what are these parameters? Okay. These three are the hyperparameters related to training time and performance of the neural network. Training time of the neural network and performance of the neural network. Okay, let's discuss them one by one. Batch size, number of epochs, and learning rate. Okay, let us discuss batch size first. To enhance the speed of learning process, your training data set is divided into different subsets, which are known as a batch. Your training data set, first let me tell you, your data set is first divided in two parts. I think we discussed this earlier, training set and testing set. And this training set is further divided into different subsets, which are known as batch. The batch size can impact the generalization performance of the model. Okay. The batch size can impact the generalization performance of the model. A larger batch size may result in better generalization. Allowing the model to average over more examples and reduce the model's weight variance. It reduces the model's weight variance because it allows model to average over more examples, because batch size is larger. So there are more data samples involved in that batch, and it allows model to average over more examples. So it would be there would be a better generalization, and this reduces the model's weight variance. However, very large batch size can also cause the model to converge to a suboptimal solution. Batch size may allow the model to perform more efficiently using the available hardware, as it can better use vectorized operations and parallelization. However, larger batch size can also cause memory issues, as it may require more memory to store the gradients and intermediate activations, because batch size is larger. Okay, so as it is larger, it requires more memory to store the gradients and intermediate activations. Okay. When batch size increases, each batch naturally becomes similar to the full data set. आप जितना उसको larger करते जाओगे, तो ultimately हो सकता है कि it will be of the size of full data set, because each batch starts to contain more observations. And this means that each batch will not differ too much from each other. वो जो बड़े बड़े बैचेस है, they are not differing from each other because बहुत सारे samples है. This batches they may overlap. This means that each batch will not differ too much from others, and therefore its noise will decrease. So it's logical to use a larger learning rate for faster training time. In contrast, when a smaller batch size is used, noise increases. Thus, we use a small learning rate to offset the noise. So see how this batch size and learning rate are related to each other. So which batch size should we use? People are still researching, but we can find the answer from others. We can find the answers from others' experiences, right? Okay, fine. Experimentally, empirically, it has been shown that a larger batch size could lead to poor generalization when you experiment, right? It has been shown that I hope you can see my screen. Okay, yeah, it's there. Like it has been proven that large batch size could lead to poor generalization. In contrast, when we use a small batch size, the noise helps network to escape a local minimum and leads to higher accuracy. So it also, like, this is all about the batch size. And let me tell you that what is the good batch size. A good default for batch size is 32. Also, you may try 32, 64, 128, 256, and so on. You can gradually increase your batch size, and you can check performance for different batch sizes to determine the optimal value for batch size. So this is about the batch size. Now let us see the number of epochs and learning rates. Okay, if we talk about the learning rate, because just we related that learning rate with batch size. So I will first discuss the learning rate and then number of epochs. Learning rate is a hyperparameter in neural network that determines the step size. At which the optimizer updates the model weights during training. It determines the step size at which the optimizer updates the model weights during training. So learning rate can significantly impact the model performance. As a lower learning rate may result in lower convergence, but a more accurate model. हमें भी पता है. If you learn slowly, but you may, slow and steady wins the race. हम ऐसे बोलते हैं, right? If you learn slowly, it may be better, you may have better understanding and you may have better learning. If you learn fast, like sometimes when you read fast, when you learn fast, the understanding may be a bit poor, and you may not have good convergence, good learning. In comparison, a larger learning rate may result in faster convergence but less accurate model. So for learning rate, we usually start with 0.1 or 0.01, or we can use a grid search method, uh, which will find a learning rate value from 0.1 to 0.000000, like you can add zeros. And when the learning rate is small, you need more iteration to find minimum value. Because why you need more iterations when learning rate is so? Because learning is slow. So more iterations are when somebody is low in learning, what we do, we teach him or her again and again because learning rate is slow. So we use more iterations when learning rate is low because model learns slowly. So we need to expose model to data many more times so that it can learn slowly, right? So thus more epochs are required when learning rate is low. And that's why all these three parameters, these three parameters are related to each other, and that's why they are discussed together. Batch size, learning rate is related to batch size. Learning rate and number of epochs are also related. Right. So now let us discuss the number of epochs and then I'll take your questions. An epoch can be defined as the complete cycle for training the machine learning model, or you can say complete cycle for training the neural network. Complete cycle from first layer to from input layer to output layer. Epoch represents an iterative learning process. The number of epochs, they varies from model to model, and various models are created with more than one epoch. To determine the right number of epochs, a validation error is taken into consideration. Validation error, which we compute when one iteration gets over, we compute the error. When we compute the error, it is taken into consideration to determine the number of epochs. The number of epochs is increased until there is a reduction in a validation error. If there is no improvement in reduction error for the consecutive epochs, suppose like we are increasing the epochs and it has been observed if there is no improvement in reduction there is no reduction in error, then it indicates to stop increasing the number of epochs further. Right. So depending on a problem and random initialization, the number of epochs you need for convergence varies. Therefore, there is no, magic number of epochs that works in every situation or that works for every problem. So in practice, we often set number of epochs high and use early stopping mechanism so that the neural network stops training when an improvement coming from updating its weights does not pass a threshold. So that is how the training is carried out. Training neural network is carried out. So you can see that epoch, like usually we set high number and then we use early stop mechanism. Okay. So these are the three parameters. Okay. This is the graph related to learning rate. A small learning rate requires many updates before reaching the minimum point because you can see that. And the optimal learning rate swifts reaches the minimum point, and too large of learning rate causes drastic updates which lead to divergent behaviors because learning is very fast. So when learning is very fast, there would be many updates and that lead to divergent behaviors. So like high learning is not good, too low is also not, because too low increases the training time. It increases the number of epochs. So in turn, it increases the number, thereby it increases the training time, right? So right value, just right value of learning rate is required, but it can be set through trial and error only. There is no standard values that for any of this hyperparameter. Fine. Okay. Overfitting and underfitting, I may discuss next time because we have 5 minutes left. So I can take your questions during this 5 to 10 minutes. Overfitting and example of this hyperparameter tuning, I would like to discuss that how we experiment and set these hyperparameters. Moreover, 3 hyperparameters are yet left. We have discussed number of hidden layers, number of neurons, batch size, learning rate, and number of epochs. Yet we have not discussed activation function, optimizers, and loss functions. Okay, questions? Any question? Students,
Yes, students, chat box is also open. If you want to write
yeah,
the question also, then you can put it in chat box also.
yeah. And you were also asking me for the book. I may suggest you one book which I considered as the one of the good books. Like there are several, but as you were asking, I don't know it's a soft copy or PDF copy is available online or not. But it is one of the good book, and its name is Principles of Soft Computing by Shivan Shivanandam and Deepa. So you can refer to this book if you want to learn this deep neural, if you want to learn neural networks and other concepts related to soft computing. So it is Principles of Soft Computing by Sivanandam and Deepa. SN Sivanandam and SN Deepa. Yeah, I think chat box. Let me see in chat box. Yeah, ma'am, can you please revise slides in brief? Just okay.